In this video, we're going to discuss Cauchy sequences. So let's write down the definition. This is definition 1.3.2 in your book. So the sequence AN, that is a Cauchy sequence. If the following is true: for every positive number epsilon, there is a natural number n such that if n and m are both at least n, then the distance from AN to AM, their difference is less than epsilon. And you can compare this to the epsilon n characterization of a limit. Here in this case, we're saying that we're not saying there's some external number A that our sequence is getting close to. We're just comparing elements of the sequence to each other. So here is a proposition. I'm not sure if this is in your book, but it is worth knowing. And this is that every convergent sequence is Cauchy. And how do we go about proving this? So we direct our reader to pick an epsilon greater than 0. And let's give our sequence a name. Let's let AN be a sequence which converges, and let's name its limit. Let's call the limit A. Then by the epsilon n characterization of convergence, so by proposition 1.3.3, which is the epsilon n characterization of convergence, there is an n such that if little n is bigger than or equal to big N, then the distance from AN to A is less than epsilon over 2. Now, proposition 1.3.3 says that for every epsilon there is an n such that if little n is bigger than big N, then AN minus A is less than epsilon. But the point is you're allowed to pick any epsilon you want. We're using epsilon here and epsilon in the statement of proposition 1.3.3 because there's only so many Greek letters to work with. But we can go ahead and say that the epsilon we're using here is twice the epsilon in proposition 1.3.3. This is something that happens in mathematics all the time. And then by the triangle inequality, if M and N are both bigger than N, then N minus AM, that's at most AN minus A, and then A minus AM, and then those are both less than epsilon over 2. So we're left with AN minus AM being strictly less than epsilon, and that's precisely the definition of a Cauchy sequence. So this is proven. And a little bit more interesting is the following theorem, which is the same proposition in the opposite direction. This is theorem 1.3.13 in your book. And this says that every Cauchy sequence in the real numbers converges, and let's specify to a real number. And so how do we prove this? So let's let N be a Cauchy sequence. And then we are going to use the definition of Cauchy sequence. We're not proving that something is Cauchy. We're using the fact that something is Cauchy. That means we get to pick epsilon. So the first thing I want to do, the first lemma as it were, claim this sequence is bounded. And then the proof of the claim and we're writing it like that because we're going to use the claim to prove that the sequence is convergent. So we're going to pick our epsilon. We're going to let epsilon equal my favorite number, which as it happens is 6. And we're going to let n be such that if n and m are bigger than n, then an minus am is less than 6. By definition of Cauchy sequence, and such an n exists. And we're going to let capital A be, we're going to take A1, A2, up to AN. That's finitely many numbers, so it has a maximum, and we're going to go ahead and add our 6 to it. If n is less than or equal to n, then an is less than or equal to capital A by definition. And if n is bigger than big N, then an, triangle inequality, an minus a, let's say capital N, plus a capital N. And we said this is at most 6 plus the absolute value of an, which is less than or equal to a. So an is less than or equal to capital A for all n, and that completes the proof of our claim. All right, so we've seen that every Cauchy sequence is bounded. And now let's get back to our main job, which is proving that these things converge. By the Bolzano-Weierstrass theorem, that was the big complicated one we had to prove a few lectures ago. This sequence has a convergent subsequence. and it's convergent, so let's give its limit a name. Let's say a sub n sub k converges to a. And then we direct our readers to pick an epsilon greater than 0. We're going to let n1 be such that if n and m are both bigger than n1, then an minus am is less than, we're going to want a half an epsilon because we're going to be doing two things with this. So n1 exists because the sequence is Cauchy. Then we're going to let n2 be such that if k is bigger than n2, then a minus a sub n sub k is strictly less than epsilon over 2. N2 exists because our subsequence is convergent and converges to A. All right. We're going to let capital N be whichever of these two things is bigger, N1 or N2. And this happens a lot in analysis. You've got two things that you need to happen. They both happen eventually. So then you would just wait until eventually. You just go with whichever one is bigger. And so we're going to try to show that this is the n in the epsilon n characterization of convergence. So let's suppose n is bigger than or equal to our big N. So we direct our reader to pick a little n that satisfies this condition. Then an minus a by the triangle inequality is an minus, okay, we need a point in our subsequence. Actually, let's name this am, not an, because we're already using n for a bunch of other things. So now we need a point in our subsequence. So let's just take the point in our subsequence that has the same index. And then a n sub m minus a. And now it's a pretty straightforward induction argument to show that, remember, to be a subsequence, the n sub m's have to be strictly increasing. So n sub m can't be any smaller than m, which is at least n, which is at least n1. So am minus a n sub m, that's at most epsilon over 2. And also, m is bigger than or equal to n, which is bigger than or equal to n2. So a n sub m minus our target a is less than epsilon over 2. So if m is bigger than or equal to n, then a sub m minus a is less than epsilon. So our sequence a sub m converges to a. In this video, I'm going to say one last thing about real numbers as compared to rational numbers. So notice we've proven the following three propositions. If you've got a bounded increasing sequence, then it converges. Every bounded sequence has a convergent subsequence, and every Cauchy sequence converges. And I want to emphasize, I don't think I actually said this, but it's implied that these were all about sequences of real numbers. And none of these results work in the rational numbers. This is another reason why we need the real numbers. So here is an example. Let's define the following sequence. We're going to let Q1 be 1, and we're going to define this recursively. Qn plus 1 is 3 times Qn, and then you add 4, and then you divide by 2 times Qn plus 3. And so the sequence of Qn's, we've got 1, you plug in 1, you get 7 over 5, you plug in 7/5, it's a lot of arithmetic, but you get 41 over 29, you get 239 over 169, and so on and so forth. And I'll point out that if you start out with a positive number, Q1 is positive, Qn plus 1 is always going to be positive, 2Qn plus 1 plus 3 is always going to be positive, so you're never dividing by 0, so you can always do this. So I'm not going to write out the proof, but the following things should be pretty clear. Qn is, in fact, since Qn is positive, it's always going to be at least 1. Also, Qn, that's less than, we've got 3Qn plus 4, n plus 1, that's 3Qn plus 4 over 2Qn plus 3. We can make that 4 into a 4.5. We just made it a little bit bigger, and notice this divides out to 3 halves. So we've got our Qn's, they're bounded above and below, so this is certainly a bounded sequence. And Qn is rational for all Q, for all N, sorry. You start out with a rational number, and then this multiplying and dividing and adding thing that we're doing, that's not going to stop it from being rational. And then something a little bit trickier. Let's write 2 minus Qn plus 1 squared. Little bit of algebra that all of you who can check comes out to 2 minus Qn squared over 2Qn plus 3 quantity squared. So if Qn squared is less than 2, and certainly Q1 squared is less than 2, then so is Qn plus 1 squared, also less than 2. Then, because Qn is at least 1, your denominator is at least 5. 2 minus Qn plus 1 squared is strictly is less than or equal to 2 minus Qn squared over 5 squared. So that's 1 over 25. 2 minus qn squared. And you can make that 1 over 25 squared, 2 minus qn minus 1 squared. Then keep going. You get it 1 over 25 to the nth power, 2 minus q1 squared, is 1 over 25 to the n. So qn squared is converging to 2. And one last thing to notice, qn plus 1 minus qn. Another leap of algebra, 2 over 2qn plus 3 times 2 minus qn squared. Since qn squared is less than 2, this is strictly positive. So our sequence of qn's is strictly increasing. All right, so this is a bounded increasing sequence. And it's not too hard to check that it is Cauchy. And so by all these theorems, it converges in the real numbers. But the thing it converges to has to square to 2. The square of the limit has to be the limit of the squares. So it converges to the square root of 2. So if all we have are the rationals, if we didn't have the real numbers, if we just had the rationals, this would be a very nice sequence, Cauchy strictly increasing bounded, that didn't converge. And in analysis, we love our convergence. You like having sequences that converge. It's something that's going to be very important to us. So this is another reason why we need the real numbers, because this is the only way we can make a sequence like this converge. In this video, we're going to talk a little bit about what it means for a limit to be infinite, for a sequence to converge to infinity, and then we're going to talk about limit supremum and limit infimum. So here is our first definition. So we say that, so we've got a series of real numbers, and we say that our series converges to infinity if, and now this is sort of like an n definition, but instead of using small numbers epsilon, we're going to use big numbers r. So for every real number r, there is a natural number n, such that if little n is at least big N, then rather than being a distant epsilon to infinity, that doesn't make sense. So we just write an is bigger than rr. And here is a proposition. So let's say we've got an increasing sequence. And we remember that bounded increasing sequences converge. And now that we've defined what it means to converge to infinity, we can say just flat out all increasing sequences converge. It's just some of them converge to infinity. And actually, most of the work is proposition 1.3.7, which is the proposition that says bounded increasing sequences do converge. So let's write down on our proof. So let's suppose a sub n does not converge to infinity. That means, so a sub n converges to infinity if for every real number capital R, there is a natural number n such that if little n is bigger than big N, then n is bigger than R. That means it is false that, then let's color code this for every real number R, there is an N. Or rather, let's say there exists such that if n is at least big N, then an is bigger than R. So now what we're saying is that for every real number R, this statement in red is true for every real number. So if an converges to infinity, then for every real number R, the statement in red and true is true. So then we can convert the statement in green. We're going to basically removing the E. It is false that's backwards one step. So there exists a real number R such that, and then we write it is false that. So for every R in R, the red statement is true. The negation of that is there is some R in R. There is at least one of them such that the red statement is false. So I'm going to write the red statement is two pieces, a green bit and a blue and another red bit. So now we need to negate this second substatement, this there exists an n such that if little n is bigger than big N, then an is bigger than r. So we can do the same trick again. There exists an n and n. The negation of that is that for all n, the thing in red is false. So we copy down the thing we've already dealt with. And then we just need the thing in red to be false. And actually, I'm going to restate this if then statement. I'm going to try to write that as a for all. So we say for all n bigger than n, it is true that at n bigger than r, so then we just this up like so. There exists a real number r such that and for all natural numbers n, and then r for all n greater than n turns into a there exists a n greater than n such that and then the negation of the statement in red, the negation of an is bigger than r, an is less than or equal to r. But our sequence is increasing. So if little n is bigger than big N, then a big N is less than or equal to a little n. So for all n and n, there is a n bigger than, a little n bigger than n such that a little n is less than or equal to r, but that is also bigger than or equal to a big N. So an is less than or equal to r for all n. Thus, our big R is an upper bound. Our sequence is bounded above, and so it converges by proposition 1.3.7. And that is the proof of that proposition. As we see, most of the work is done by proposition 1.3.7, and most of what I put you through was just carefully figuring out how to negate what it means for this very complicated definition to be false. In this video, we're going to talk about the limit supremum and limit infimum of a sequence. And I think, first of all, I'd like to write down what it means for the supremum or infimum of a set to be infinity. It's pretty intuitive, but let's write it down anyway. Let's let A be a subset of the real numbers. We say that the supremum of A equals infinity if, well, we don't want A to be the empty set and A has no upper bound. And you can put this in other way for every real number R. R is not an upper bound, so that means that there is an element of A with which is strictly bigger than R. So that means that the elements of A can get as big as you want. All right, so now let's move on to limit infimum and limit supremum. This is sort of really the point. This is the main definition of this video. Let AN be a sequence of real numbers then we define the limit supremum of the AN. That's the limit as n goes to infinity, and then the supremum of, we're going to take the sequence and cut it off at n. Limit infimum, it's the same thing, except we've got an infimum instead of a supremum. So you can visualize that. So here's an example. Here are AKs bouncing around. We take the supremum of all the points. We get this line. Then we take the supremum of, we leave this point out, we get the same supremum, we leave this point out, and then suddenly the supremum is down here. And then we throw out this point, and then our supremum is a little bit lower, and so on and so forth, and we see our supremum is tending towards this level. And so that's how the limit supremum works. And there's a proposition that I think is worth knowing. So let's let n be a sequence of real numbers. Then there are all kinds of sequences that don't have limits. 1, minus 1, 1, minus 1, 1, minus 1. That's a sequence that doesn't have a limit. It's not even that it has a limit, but it's infinity, not a real number. There's just no limit. But it does have a limit supremum. The supremum of the tails is 1. The infimum of the tails is minus 1. So any sequence has a limit supremum and a limit infimum as long as you allow them to be infinite. It's sort of like the result we saw in the last video where the limit supremum, where the limit of an increasing sequence always exists, but as long as you allow them to be infinite. And here is how we prove that. So we're going to let x sub n be the supremum of the AKs such that k is bigger than n. And then we have to be a little careful because xn could be infinite. If our sequence is the sequence 1, 2, 4, 8, 16, 25, 36, and so forth, then the supremum is infinity, and it's going to stay infinity no matter how many bits you throw off. So if xn equals plus infinity for all n, then limit supremum of the ANs exists and equals infinity. I suppose technically we haven't said much about what it means to be the limit of a sequence if you allow elements of the sequence to be infinity, but in this case, either you're eventually finite or you're infinite forever. So that's fine. So if x sub big N is less than infinity, let's notice x sub n plus 1, or actually let's say x sub n, that's the supremum of an and all the AKs such that k is bigger than n is at least n plus 1. And if we throw out our first set, if we just look at the AKs for k bigger than n plus 1, throwing something out can't make the supremum bigger, it can only be smaller, so we've got xn plus 1. So the sequence of xn's is a decreasing sequence. And so we're going to, in particular, xn is so xn is less than or equal to x big N is finite for all n bigger than big N. And by the previous video, the Lin soup has to exist. One more proposition I'm going to write down whose proof is an exercise. This is proposition 1.3.16 in your book. Let an be a sequence of real numbers. Then we've seen that the limit supremum and the limit infimum exist, but it's not too hard to show that the limit supremum has to be bigger than the limit infimum. That's just because they're based on the supremum and infimum of the same set. That's your sequence is bounded above if and only if the limit supremum of the ANs is finite. Third fact is that AN converges to A if and only if the limit supremum of the ANs is equal to the limit infimum of the ANs and is the limit. So if you've got a limit, you've got a limit supremum, you've got a limit infimum, and they're the same, and they're all the same thing. If your limit infimum and limit supremum are the same, you've got a limit, and if they're different, you don't have a limit. And fourth part of this is that if AN is less than or equal to BN, that is if you've got two sequences and a point, you compare them term-wise, you compare them point-wise, and the A's are less than the B's, then the limit supremum of the ANs is less than the limit supremum of the BNs, and the same thing is true for the limit infimums.